Welcome to another deep dive. This time, into the world of topological quantum computers.
Sounds pretty complex.
It is, but also fascinating. It's this crazy intersection of physics and computation. Like it could totally revolutionize stuff. Drug discovery, cryptography, even more. And our guide for this deep dive is an essay by Yorgo Schneeppat. He really gets into the nitty-gritty.
So, before we dive in, a super quick recap for anyone who needs it. Quantum computers, how are they different?
Right. Quantum computers use qubits. Our everyday computers, they use bits, right? 0, 1. But qubits, they're like chameleons. They can be in multiple states at the same time.
That's superposition, right? One of the big things that makes quantum computers so powerful.
Exactly. And because of that, they can tackle problems that would take classical computers forever. We're talking billions of years. Quantum computers could potentially do it in a reasonable time frame.
That's incredible when you think about it. But Schneeppat mentions a challenge: decoherence.
Yeah, decoherence. The Achilles heel of quantum computing.
Qubits, they're super sensitive. The slightest disturbance messes them up, causes errors. That's decoherence. It's been a huge roadblock in building reliable quantum computers.
So where do these topological quantum computers fit in? They sound like they might be the answer.
They might be. See, topological quantum computers, they use topology. That's a branch of math dealing with shapes and their properties.
Okay, I vaguely remember that from school. But how does that help with quantum computers?
Well, think of it this way. Topological properties, they don't change, even if the shape gets deformed. So instead of encoding information in the fragile state of a single qubit, topological quantum computers use the global properties of a system. Schneeppat calls these systems enneins.
Enneins. Sounds kind of sci-fi, doesn't it?
Oh, a little bit, but it's real. They're these quasi-particles. They exist in two-dimensional systems, and they have this unique behavior. They can be braided.
Braided. Like
Wow.
hair.
Yeah, kind of like that. Imagine weaving threads into a tapestry. The way you intertwine those threads determines the final pattern, right? Well, we can braid enneins by moving them around each other in specific paths. That's how we perform quantum computations.
So we're weaving computations into the very fabric of these Ennean systems. It's like some next-level coding.
It is. And the coolest part, because the information is encoded in the global topology of the system, local disturbances don't really affect it.
It's like building a quantum computer with built-in error correction. Genius.
Right. Yorgo Schneeppat also talks about certain materials that they're using to build these computers.
Yeah, he does, like topological insulators.
Exactly. They're cool. They act as insulators on the inside, but they conduct electricity on their surface. It's those surface states that can host enneins. And they're topologically protected. So we need the right materials for this to work. It's not just the theory.
Absolutely. So it's this super complex dance between theory and material science.
Yeah. Schneeppat also talks about superconductors. Researchers are really interested in these things called Majorana quasiparticles.
Majorana quasiparticles, what are those?
They're kind of unique. They pop up in certain superconducting systems, and they have this weird property of being their own antiparticles. Imagine that.
I can't even wrap my head around that.
Yeah.
But they can be used to create super stable qubits, right?
That's the idea. It's all pretty mind-blowing. We're talking about manipulating these teeny tiny particles at crazy low temperatures, and somehow we're using them to do computations.
It's amazing. But are we actually making progress? Like, are we actually building these systems?
Yeah, actually, there's been a lot of progress lately. Researchers have actually created and manipulated enneins in labs.
That's incredible. But I imagine there are still some big challenges, right? Like scaling these things up from the lab to something useful.
Oh, for sure. That's a big one. Schneeppat talks about that too. Figuring out how to get to hundreds or even thousands of qubits. That's what we need to tackle real-world problems.
So we're still in the early stages, but it sounds like there's a path forward.
Definitely. And the potential is huge. We could be talking about revolutionizing entire industries. Drug discovery, materials science, cryptography, even more.
It's mind-blowing to think about.
It really is. But before we get too carried away, maybe we should take a step back and look at where topological quantum computers could have the biggest impact. What applications are researchers most excited about?
Yeah, let's dive into that. First up, cryptography.
Of course. Earlier, we talked about how quantum computers could break current encryption methods. But Schneeppat says that topological quantum computers could actually be the solution. They could help us develop new, ultra-secure encryption algorithms.
So they're both the problem and the solution. That's kind of ironic.
It is, but it highlights how powerful this technology could be. And beyond cryptography, Schnepphat points out that there's huge potential in drug discovery and material science.
Yeah, being able to simulate the behavior of complex molecules accurately. Imagine that.
Exactly. We could design new drugs, new materials with properties we haven't even thought of yet.
It's like unlocking a whole new level of control over matter. It's incredible.
It is. But as Schnepphat reminds us, there's another side to all of this, the societal and ethical implications.
Right. We can't just focus on the shiny new tech and ignore the potential downsides.
Exactly. We need to think about the impact on jobs. What happens when quantum computing automates tasks that humans currently do? And how do we ensure that everyone benefits from this technology? We don't want to increase inequality.
Absolutely. And what about misuse? This is powerful technology.
Yeah.
We need to think about how to prevent it from being used for the wrong reasons, like breaking encryption for nefarious purposes.
You're right, these are complex questions, but they're questions we need to answer now. Before it's too late, we have to be responsible with this technology.
Well said. Topological quantum computers have the potential to change the world for the better, but we need to be mindful of the potential downsides and be prepared to address them head on. Let's take a short break. When we come back, we'll delve even deeper into the future of this mind-blowing technology. So we've talked about the potential, but how are researchers actually making these topological quantum computers a reality? What are they working on right now?
Well, Yorgo Schneppert, in his essay, highlights a key area, improving the techniques for creating and manipulating anyons. Remember those quasi-particles? They're at the heart of it all, and we need to control them with insane precision.
Right. It all comes back to those anyons. Earlier you mentioned braiding them is how we perform computations. But how does that actually work in practice? It's hard to imagine physically moving around these tiny, tiny particles.
It is pretty wild. Researchers are trying different things. One approach uses superconducting nanowires. They're like little highways. For Majorana quasi-particles, we can move them around, braid them in very specific ways.
It's like a choreographed dance for quasi-particles. Sounds super tricky. What are some of the other big challenges?
Well, Schneppert mentioned scaling. Right now, experiments are happening with just a few qubits. But to really use these computers for big problems, we need way more. Hundreds, thousands, maybe even more. And that's not easy, especially while keeping everything stable and precise.
Yeah, it sounds like a huge undertaking. What about beyond just adding more qubits? What other advancements are on the horizon?
Schneppert touches on this too, hybrid platforms. It's an exciting area. Right now we're talking about topological quantum computers as standalone things, but what if we could combine them with other quantum computing technologies or even classical computers?
Interesting, like a team effort.
Yeah, imagine using light to send information between topological qubits. That could be incredibly fast and efficient.
So we're talking about a network of quantum computers, a quantum internet.
Exactly. Each computer could specialize in a different task, and when you connect them all together, the computational power, the flexibility, it'd be like nothing we've ever seen before.
It's mind-blowing.
Mhm.
But let's come back down to earth for a second. What are some concrete milestones to look for? Things that'll tell us we're moving toward these large-scale, practical, topological quantum computers.
Well, first, progress in scaling up, like we talked about. Getting to hundreds or thousands of qubits while maintaining control and stability, that's huge. Another one is fault tolerance. Can we build systems that can catch and fix errors without sacrificing efficiency?
So it's not just about quantity. It's about quality, too. Makes sense. Anything else?
Keep an eye out for new algorithms, one specifically designed for topological quantum computers. We're talking about a whole different type of hardware. We need algorithms that can really take advantage of what it can do.
It's like a whole new programming language tailored for these unique machines. Pretty cool.
It is. And lastly, watch for progress in integration. Connecting topological quantum computers with other systems, classical computers, user-friendly interfaces for controlling and programming them, maybe even those quantum networks we talked about.
So it's a multi-pronged challenge. Hardware, software, integration. To make these computers a reality, it sounds like it'll take collaboration across a lot of different fields.
You got it. It's a massive effort, but the payoff could be huge. So worth it.
Totally agree. Now, before we move on, I want to circle back to something you mentioned earlier, unexpected discoveries. Schnepphat talks about that too. It's exciting to think that we might stumble upon things we never even imagined.
That's the beauty of science. When you push the boundaries, you never know what you might find. For example, there's a lot of interest right now in the connections between topological quantum computing and cosmology.
Cosmology, that's a big jump. What could those two possibly have in common?
There are some clues, hints that topology could help us understand some of the universe's biggest mysteries. Dark matter, dark energy, the Big Bang, maybe even parallel universes. It's early days, but the possibilities are pretty captivating.
Wow. So studying the tiniest particles could help us understand the vastness of the cosmos. Incredible. What about here on Earth? Any chance of unexpected discoveries closer to home?
Absolutely. Topological quantum computers could revolutionize how we understand complex systems. Biological systems, for instance. Imagine simulating how diseases work, or finding new treatments, or modeling things like financial markets or social networks.
So we could use these computers to understand the world around us in a whole new way. That's both humbling and exciting.
Exactly, and those are just a few examples. The potential is limitless. Who knows what we'll find as we keep exploring this new frontier of topological quantum computing?
We've covered a lot of ground. The technical challenges, the potential for hybrid systems, unexpected discoveries. And it's clear this is a huge collaborative effort.
It is. Topological quantum computing isn't just a scientific pursuit. It'll affect all of us in ways we can't even predict.
It's so true. So as we head into the last part of our deep dive, I want to leave our listeners with something to think about. How do you see this technology shaping our future? And what role do you see yourself playing in this quantum revolution? We'll be back soon with our final thoughts. Well, we've been through a lot, this world of topological quantum computers. NEs, breeding, the quantum internet. It's pretty amazing stuff.
It is, and Schneppat did a great job laying it all out. Ambitious, but realistic.
Yeah, he did. And it really hit me that this isn't just about faster computers. It's about pushing the limits of what we know, maybe even solving some of the biggest problems we face.
Definitely. We've talked about some pretty incredible potential applications, drug discovery, unbreakable encryption. But Schneppat's right. We need to be thoughtful, responsible.
100%. We talked about jobs, access, the potential for misuse. It's not just about the technology itself, it's about how we use it.
Right, and it's important to keep in mind this is all still pretty new, a lot of research and development to go before these computers are part of our everyday lives.
True. But it's a future worth working towards, and it's happening right now. Brilliant people all over the world are making it happen.
Exactly, and that's what's so inspiring. It's not just a few people, it's researchers, engineers, policymakers, even the public. We all have a role to play.
And to anyone listening out there, you don't have to be a scientist to be a part of this. Be curious, ask questions, get involved in these conversations about technology.
I love that. The future of topological quantum computing. It's being written right now, and we're all part of the story.
What a great way to put it. This has been an awesome deep dive. Thanks for joining me.
It's been my pleasure. To everyone listening, keep exploring, keep learning, and never stop imagining what's possible. The future's wide open,